Hi, this is Sara, and I'm your chemistry tutor. This lesson is from the AS Chemistry Crash Course. You can join the full course by clicking the link in the description. And feel free to comment if you have any questions, because I'm here to help you. You can also join the live launch this Easter, because that will be your first step towards exam preparation. Enjoy and learn. Hi, and welcome to the third lesson of this course. Today, we go through the topic of amount of substance, where we look at all the equation and we will look at their application as well. So you know the layout of the lesson, and so let's move straight into the content. So the first important thing is that you're confident in writing down balanced equation, but also ionic equation. Okay, so let's have a look at the method to do ionic equations. And here we'll walk you through the example I already did. So we have a typical reaction of metals, so displacement reaction. One metal takes the place of another metal. If we want to work out the ionic equation for this, we could do this method, which is like splitting the ionic equation. In fact, what we can do, we could split the ionic compounds into their component ions. So the important thing to consider is that you would write as ion only ionic compounds in the reactant, and in the product only ionic compounds that are in aqueous state. So notice here zinc stays as the metal, copper sulfate. It's an ionic compound in aqueous solution, which means that the ions are free to move. Same thing for zinc sulfate, and copper stays as an element. Those repeating ions, they're called the spectator ions, and they will cancel out, because if we just add up the equation, those would be repeating, so they just cancel out. And here you have the overall ionic equation. There is another method, and this is thinking about what is the focus of the reaction. So this is useful for a reaction that you can recognize. For example, if you have a neutralization or a precipitation reaction, because neutralization reaction, think about it. What is the point of that reaction? Well, the neutralization product. So for example, if we have a base like an oxide and an acid, they will form a salt and water. What is the neutralization product? It's water. So in this case, we would just write the ions that make up this neutralization product. And that would be simple. Obviously thinking about, okay, where does the oxygen of the product comes from, the oxide, and where does the hydrogen come from the acid. The other type is a precipitation reaction, where again we focus on the solid product. So in this case we have silver chloride being the solid. So the ions that make that up would be the ions in the ionic equation. Okay. If we want to use that first method for those reactions, it's really, really important to remember what we split and what not. Because remember that we do not split covalent compound, solid ionic products, and their elements. Okay, so now it's your turn. Write the ionic equation of those two. Yeah, pause, try it, and then play again. And I will walk you through. If you're ready, let's do it together. So in this case, because in the first one we don't have a clear focus of the reaction, what we can do is the splitting ion method. So we know that chlorine is an ion, is a covalent compound, so it's not going to split. Second, we have potassium and bromine, aqueous ionic compound in aqueous solution. So this, yes, it will split. In fact, we will have two of the potassium. We can work out the chart from their formula, or we can look at the periodic table, and notice that the ratio stays. Also for the bromine, it will be Br minus. Then on the product side, we have Br2, so that's an ionic covalent compound, so it does not split, and we have 2 KCl. So that's an ionic compound, aqueous solution, so it will split, it's not a precipitate, and we will have 2 of the Cl minus. Notice what cancels out, so the 2 potassium are our spectator ions, so the overall equation will be chlorine plus 2 of the bromide ions to form Br2 and 2 of the chloride ions. Okay. For the second equation, we can, if we observe it, it's a precipitation reaction because we have a solid product. So we can, and we know that all of the other ions will split because they are in aqueous solution. So we can think that the ions that will make up the ionic equation are the same that will do this focus of the reaction, so the ionic product. In fact, we can work that out pretty easily. We would have silver plus, we know its charge from their ratio with the iodine, and iodine as I minus, because we know its ratio. We could also include the state symbols, which will be the same as the ones in the equation. Okay, I hope ionic equation makes sense for you. So we're ready to move into another very important concept, which is the mole ratio. So the mole ratio is the comparison between the number of moles in a balanced equation. Okay, and it's used to predict amount of substances. It's really, really important because this is the base of every calculation and comparison of substances. So we can get the mole ratio as the coefficient in a chemical equation. So this is, for example, if we look at the balancing that we had before, chlorine with potassium bromide, the first equation there, we can see that the chlorine is 1. And the bromide has that big 2 in front, which means that their ratio is 1 to 2. So for every mole of chlorine that it's formed, we would have double the amount of potassium bromide that reacts with it. Okay, which means that if we have 0.5 moles of potassium bromide, how many of chlorine would we have? Well, we need to remember to apply the same change as the ratio. Going from 2 to 1, we divide it by 2. So we will do the same, divided by 2. So we will have 0.25. But the ratio is also important in the number in a formula. So for example, if we have sulfuric acid, the ratio with its hydrogen ion is going to be 1 to 2 because in the formula we have twice the number of the hydrogen. Okay, so the moles work in the same way. 0.25 for sulfuric acid, we will have double the amount of the H+, so we will have 0.5. This is important because I will repeat this many, many times. Yeah. Whenever we have the any type of calculation, this is the first thing that should come to you, mole ratio mole, because this always gives you the starting point of a calculation. And now we will go through step by step all of the equations that you need to know. So let's look at the first equation of moles that relate to its definition, because 1 mole, remember, it's a new unit of substance, and this contains 6.02 times 10 to the 23 atoms. So what it means is that there are this number of atoms or even particles in general per mole. Okay, that's why all of the elements, they can be compared, all of the amount of substances can be compared in moles, because it's just relative to the number of atoms. So the triangle for the equation that refers to this definition is the green one, where the Avogadro's number, which is that 6.02 times 10 to the 23, times the moles, it gives us the number of atoms, ions, or molecules. We will see some examples for that. Okay. The second definition is the one that relates mass and MR, because the mole is also the amount of substance that contains the same mass in grams as the relative atomic mass. And this is an equation that I hope you will all remember, that is mass divided by moles is equal to MR. Or remember, as mole is equal to mass over MR. Anyway, you know the unit for the MR, which is grams per mole. Sometimes you're given that even in the question. And this translates into grams per means divided by, so grams per mole. Okay, let's see the application to one of the question. So let me get the laser. Okay, so remember what we said, that 1 mole contains this specific amount of either atoms, ion, molecules. Okay, so find the number of ions in 0.5 moles of KCl. The first thing is, remember that moles ratio moles. It will come up in pretty much all questions. Moles ratio moles. First step, find the moles. We have it, 0.5 moles of what? KCl. Second, the ratio. The ratio also applies in this case because 1 mole of KCl contains 2 moles of ions, so that ratio is 1 to 2, which means that we can find the number of moles of what we're trying to find, which is the number of ions. So it would be 0.5 times 2 equal to 1. So the number of ions will be the same as the Avogadro's constant in this case. Now it's your turn. Are you ready to try? Pause, and then when you're ready, play again, and they'll give you the solution. If you're ready, let's go. Which of the following contains the most chloride ions? Okay, well, we're talking about, again, the number of ions. First thing, moles, ratio moles, that always, is always relevant. In fact, we need that. But notice that we have numbers and then we have name of compound. That's so confusing. So if you can have something visual to relate to, have it. Mostly for the ratio, we either need a balanced equation or the formula. In fact, here, the first thing I would suggest you to do is write down the formula of this. And you can do it by looking at the periodic table if you're not sure. Aluminium chloride has a formula of AlCl3. Calcium chloride, it's CaCl2. Hydrochloric acid is HCl. Sodium chloride is NaCl. Okay, so how to approach this question? First thing, the number of chloride ions, which means that the ratio can be different. For the first one is 1 for the AlCl3 to 3 chloride ions, because there are 3 chloride ions in each molecule. In the second one, we have a 1:2 ratio. In the third one, 1:1. In the fourth one, 1:1. Mole ratio. So we can find the moles of the chloride ion, but we're given volume and concentration. So this is another equation that we will come across a bit later if you're not familiar yet. And otherwise, I hope you can relate it with the unit, because this mole per decimeters cube, this is the what this unit translates to. In fact, that's equal to the concentration, volume, and moles. So we can find the moles for each. We can convert each of this volume into decimeters cubed by dividing by 1,000. And then we can times it with the concentration to find the moles. Okay, so that's the first thing. Find the moles of each, and then, well, you don't really need it. You need to do the ratio and the moles again, but you don't need to find actually the number of atoms, because you know that the biggest mole will give you the most, the both number of atoms. Okay, so after that, if you do the correct calculations, the one that has the most chloride ion will be this one. But notice how that mole ratio mole always works. Okay. I hope it's clear. If not, you can ask me any question in the comments or in the classroom, and we can go into the next calculation with the other unit that we've seen before. So remember what we said, that the moles is the amount of substance that contains the same mass in grams as the relative atomic mass. So what we can do is, let me get the laser. Find the maximum mass of KCl that can be formed from 10 grams of chlorine and excess KBr. So excess means that we don't need to worry about this amount, we just need to worry about the amount of chlorine. Moles ratio, moles always. So find the moles using this equation, mass over MR. You need to find the MR. So for a diatomic atom, remember that we have 2 of them. So it would be, in this case, the chlorine times by 2. And we get the moles. Ratio, for 1 chlorine, we get 2 potassium chloride. Okay, so you know this by the balancing of the equation, always the big number for when we're comparing different substances. So we can find the moles again by timing it by 2, and then the mass by rearranging this equation, doing moles times the MR. MR, you can find it separately or all together in the equation, as you prefer, and we will get the mass. Okay, so I hope this is clear, and now it's your turns. Now we need to apply both equations. Please pause and then play again when you're ready. And if you are, let's do it. First, we have the mass and we have the MR. Guess what we can find? The moles. So moles is equal to mass over MR. This will give a certain value. Yeah, probably like, I think 0.1. But this will be the moles of what? Calcium hydroxide, because that's what you have the mass of. So it's really important that if you do this as an open question, you could write in a bit more detail whatever you're finding. Yes, so that's what I would do if it was an open question. First, what do? You find the moles of calcium hydroxide. The labels are so important, to keep a track of what you're finding. And so how do we find the moles? We do mass over MR looking at the triangle. So it's 7.41 divided by 74.1. Okay, and that should be equal to 0.1, doing top of my head, moles. Then what do we need to do? Although it's the ratio. Sometimes we don't need this, so you can just check a ratio. Oh, it's 1:1, that's fine. But in this case, it's not, because the total number of ions. How many ions do we have here from your knowledge of bonding? We have calcium, and then we have hydroxide, which is minus, but we have 2 of them. So total, we have 3 ions. Therefore, the ratio will be 1 to 3. So the moles of our ions will be equal to that 0.1 times 3, so it will be 0.3. And how do we get the Avogadro's, how do we get the number of atoms? Over here, Avogadro's number times the moles. So I think it should be this times by 0.3, and this would give us this. Okay, good. So the next equation that we look at is concentration. Before we look at the worked example, let's look at the definition of concentration. Sometimes it's also called molar concentration because it's the amount of moles per unit volume. The units are decimeters cube. In fact, the unit of this concentration is mole per decimeter cube. So that translates into moles divided by volume. So the conversion is really important because centimeters cube is actually equivalent to millimeters, which is something that it's easier to measure in the lab, while decimeters cube is equivalent to liter. Okay, so to convert this centimeter to decimeter, we have to times it by 10 to the minus 3 or divided by 1,000. While decimeters to centimeters, the opposite. It's times by 1,000 because the cube corresponds to that to the power of 3 in the difference in unit. Okay, in fact, if we look at this example, read it for a moment and then I'll walk you through that. So the first thing to think about is the unit. Okay, never forget them because it's a really easy mistake. And you can just notice, okay, whenever you read the equation, whenever you read the question, the equation is right there in front of you. So just learn how to notice the unit while you read the equation and you'll never forget the unit. So we can convert that or just as a habit, first thing to convert the unit of volume. In fact, if we have 20 centimeters cube, it will be 0.02 decimeters cube. Then this step of mole ratio mole is always the same. In fact, we can find the moles. Remember, you can find the moles of only the thing that you have the concentration of. So in this case, it's the sodium hydroxide, as we have it here. So we can get the moles. Ratio from the equation 1 to 2. So we can find the moles on, in this case, sulfuric acid, and then we can find the moles of that by dividing by 2. And having that, we can look back at the question at what we want to find, which is the volume of sulfuric acid. So to find the volume, we rearrange the equation as mole divided by concentration to get the decimeters cube, which we can convert back into centimeters cube if it's required. Okay, so the important things to remember are the units, how to rearrange the equation, and if you don't remember the equation, the units tell you because mole per decimeters cube translate into mole over volume. Mole ratio mole, it's always useful. So now it's your turn. Let's try this exercise. So first pause and then let's do it together. If you're ready, we can go through that. Okay, so we want to calculate the mass present in 100 centimeters cube of that amount of volume. Okay, so first of all, we can notice the values that are given. We have volume and concentration. So what can we find? If you can look at the unit again, that helps. We can find the moles. So the moles of calcium hydroxide. We can either look at the unit or rearrange the equation, if you remember, is concentration times volume. Concentration, it's a 0.1. I would suggest you to write the unit always because this helps you understanding if you converted them or not. In fact, we can convert it all together in the equation, or we can do it all we can convert it before or do it in just one equation. Okay, so 0.1 times 0.1 should give us 0.001. I'm just doing it top of my head. 0.1 times, yes, 0.001. Now that we have them all, look back at the questions. I would suggest that you, as soon as you read the question, as soon as you do one calculation, then go back to that and read it again. In fact, this helps you keeping in mind what is that you're trying to find. In this case, the mass. Okay, we have the moles. Then if we have the mass, which unit can we use? Sometimes you're also given hints in the question. Here we have the molar mass, grams per mole. We know what that means, right? Mass divided by moles is equal to the MR, which means that we can find the mass by doing the moles times the MR. So in this case, would be 0.001 times 74, which would be equal to 0.074, right? 0.74. I hope this is clear. So these are calculation of concentrations. They're really, really common and useful in titrations, which we're going to look in another lesson for acid and bases, and there is going to be an extra video on back titration, because these are quite a calculation that are going to come up certainly in paper 3 as longer question. So not only normal acid-base titration, but also redox titration or back titration, which is this particular type that can be of different type of reactions, and they're really common probably in all papers. So it's important to take some time to do that. So if you're at Edexcel, there is another unit of concentration that you need to know. If not, you can skip ahead to the next calculation. If you're at Edexcel, then stay with me. So parts per million is a different unit of concentration and is the amount in a million unit volumes. Okay, so it could be of different units. It could be mass in mass. It could be volume in volume. Depends. Let's look at this example. The mass of magnesium ions in 1 kilogram of seawater is 1.3 grams. What's the concentration in parts per million? Think about what millions means. That's what I want to think. It's parts in 1 million. So if you have 1 kilograms is 1.3 grams, what this means is that you have 1.3 grams in that kilograms. And in parts per million is the amount, in this case, of grams in 1 million grams. So all you need to do is find how many times bigger is 1 million over that 1,000 grams. I like to use the proportion method, so let's see if you understand it. So what the question tells us is that there are 1.3 grams in 1,000 grams. Just like there are a certain amount of grams that we need to find in 1 million. So this is a proportion, and it's set up just like asking a question, like if there are 1.3 grams in 1 million grams, in 1,000 grams, that is like if there are that certain amount of grams in 1 million. So the rearrangement is timing the numbers at the edges, so 1 million times 1.3, and then we divide it by 1,000, which is the value here next to the equal sign. And this is 1.3 times 10 to the 3 grams, and that is parts per million. So it's 1.3 times 10 to the 3 parts per million. Okay, so the other way to think about it is that you are timing this value, by this factor. And this factor can be found as, let me write that down, as 1 million. Did I write too many signs? Yes, let me start again. So it's 1 million, so 10 to the 6, right? So this is kind of a factor. So 10 to the 6 over the 1,000 that we have here, it is 10 to the 3. So the factor, so the concentration in parts per million will be bigger by 10 to the 3. That's why this value is actually just the times by 10 to the 3. So it's finding the factor by which time, like how many times this unit concentration is bigger than the one given. So two different ways of finding it. Yeah, this is similar concept to the dilution factor. While this one is using this mathematical concept of proportion. Okay, so whichever method you prefer, apply it to this next question. So pause, try it, and when you're ready, play, and we do it together. So if you attempted it and now you're ready, let's go for it. So we have this value 0.000. So this value is really horrible to look at. So you know what I would do? I would do it in the standard value, which is 2.5 times 10 to the 5. Okay, but this is percent. Think about what that means is in 100 unit values. So we want to find how many of this there is in million. So I'm going to do it 10 to the 6 in 1 million of these values. So once again, you can do it two different ways. Finding the, let's call it dilution factor. It's not dilution factor, but it's this factor, by which we understand how many times the parts per million is bigger than the value percent that we're given here, which is 10 to the 2. And there would be 10 to the 4. Okay? Which means that our value would be that 2.5 times 10 to the 5, to the minus 5, because it's 0, times by this factor. Okay? Otherwise, you can do the proportion method. 2.5 times 10 to the minus 5 is present in 100 parts as you are given the percentage. So what is the value of this concentration in 1 million? And guess what? We will get exactly the same, 0.25. So I hope this is clear. It's quite mathy, but it's about fully understanding the meaning of the units of concentration. Okay, if that's clear, let's move on. Otherwise, make a little note of it, and during our live lessons, we can clarify and do more practice. If not, the next equation. We're talking about gas. So this is a kind of concentration unit, but it's called molar gas volume. And what this kind of gas law tells us that at room temperature and pressure, 1 mole of any gas occupies 24 decimeters cube. So this molar gas volume is 24 decimeters cube per mole. So what that means is that each mole occupies that volume. Room temperature pressure, remember, is 25 degrees, and 1 atmosphere or 298 kilopascals, and 298 Kelvin and 101 kilopascals. So if we translate this molar gas volume is decimeters cube per mole, which tells us that decimeters cube is the volume, so volume divided by the moles gives us this molar gas volume. In fact, this is the triangle to remember. Volume divided by the moles is equal to the molar gas volume. Okay, whichever way you find it easier to remember, for me is always understanding the unit, this definition. If we look at its application, let me get the later. Okay, this is the question, read it through. And one tip is that you're given the molar gas volume, or you're given room temperature and pressure, which means that this gives a hint of, okay, this is the equation to use. So read it and then I'll walk you through. Okay, guess what? Mole ratio mole, always. Moles of, well, we are given that 0.5 of this sodium nitrate. Ratio, we're finding the moles of oxygen, so that the ratio would be 2 to 1. Yeah, 2 to 1, which means that, so this is 1 oxygen. My bad. Let me correct the volume. So 2 sodium nitrate reacts with 1 oxygen. Yeah, it would be 1 oxygen, so is the other way around, 2 to 1. So you can see it from the equation. Okay, so we can find the moles of oxygen that have reacted, because remember that we want to find the moles of gas. So look at these state symbols that help understanding which are the gases that are present, because here is just oxygen, but in the reaction there could be a mixture of gases, so you need to pay attention to that. Anyway, having the ratio, we find the moles of oxygen, which was 0.5, and we divide that by 2, and then we can find the volume by doing, in this case, moles times the molar volume. Also notice how the unit cancel out. Yeah, you're given here the unit, which helps to double check that you did the right rearrangement, and we have the volume. Okay, so pretty straightforward. The equation important is the unit of volume, just like we did for concentration, and understanding which gas are you which gas are you calculating. Okay, so now it's your turn. Pause and then do it, and then press play when you're ready. And if you are, I am ready too. Well, this there is something highlighted, right? Which means how many moles of atoms. Okay, so maybe we need to use that Avogadro's constant. Okay, oh, how many moles? Anyway, in 240 centimeters cube of carbon dioxide at room temperature and pressure. Okay, so we have room temperature and pressure. That gives the hint that we need to use the molar volume equation. And the other hint is that 24 decimeters cube, that value. Okay, so what can we find? We can find the moles. So we can find the moles of what? Of what we have the volume of carbon dioxide. So you can also highlight the important things that you're given in the equation, so carbon dioxide. So moles of carbon dioxide would be 240 centimeters cube. Remember, the volume is always in decimeters cube, but they have to match. So it would be the volume 0.24 decimeters cube converted divided by 1,000 divided by 24 decimeters cube per mole. Okay, and this should give us 0.1. Let me just double check that. 0.24 divided by 24, 0.01. 0.01 moles. Okay, but that's the moles of carbon dioxide. You want the moles of atoms. That's why you have it highlighted. And it's where mole ratio more it always works, because we have for 1 mole of carbon dioxide, how many atoms do you have? You have 3 atoms, because you have 1 carbon and 2 oxygens. That's why the ratio would be 1 to 3. So the moles of atoms will be 0.03. Okay, I have a bonus for you, because let me explain it. We do mole ratio all the time, but guess what? We can do the same with the volume. Volume, ratio, volume. Okay, so think about these atoms that are reacting together. There is no mole calculation. It's just looking at the volume. The hint is to think about the limiting reagent and the one in excess. Press pause, give it a go, and then when you're ready, play again. And if you're ready, I am ready with you. So, first thing, there is a lot going on, so highlighting could help. We have 100 centimeters cube of hydrogen. Okay, otherwise we can write it here. We have 100 centimeters cube of hydrogen. Is mixed with 25 centimeters cube of oxygen. Okay, and those are the things we have. Total volume of gas present at the end of the reaction. Okay, what I'm saying about volume ratio volume is that you don't need to find the moles, because if you have 25 centimeters cube and you have 2 moles of hydrogen and 1 of oxygen, 25 centimeters cube of oxygen, which is the ratio 1, will react with, guess how much of hydrogen? Double that, 50 centimeters cube, because of this ratio 1 to 2. This is our oxygen and this is our hydrogen. Because 25 centimeters cube of oxygen will react completely with 50 centimeters cube of hydrogen. And I've started from the smallest value, because that's the more likely one, even if there is a different ratio, to be the limiting one, so the one that runs out first. So like this, we know that this total amount of oxygen will react with just 50 centimeters cube of hydrogen, which means that there is going to be 50 centimeters cube of hydrogen in excess. And then to find the amount that have reacted, so the amount of product, we use the ratio. Look at the ratio between oxygen, I'm going to write it here, oxygen and water. because that's the gas that we want to find, is 1 to 2. If we have oxygen that is 25 centimeters cube, guess what water would be? 50, because of the ratio 1 to 2. So it will be exactly 50 gas. Not sure what's happening to my pen, but it's not working. So let me tidy up a little bit. Yeah, it's a bit late, but I hope we can see it. So to repeat it, because we have 25 centimeters cube of hydrogen, of oxygen, and the ratio is 1 to 2 with our product, there would be 50, so a maximum of 50 centimeters cube of water formed. So if we have a 50 centimeters cube of water formed, and we know that we have 50 in excess, at the end, 50 of hydrogen in excess, we will get B, which is 100 the total. We have one more equation to learn for gases, and this is called the ideal gas equation. So this relates pressure, volume, moles, gas constant, and temperature. So it has a nice sound to it. PV is equal to nRT. The tricky thing about this equation are the units. Okay, so the unit of pressure, it's pascals, when the volume is measured in meters cube. Moles. Gas constant is given, and it's 8.314, 8.31 joules per Kelvin per mole, which means that the temperature has to be in Kelvin. Okay, so my suggestion is remember one set of unit, because this could also be kilopascals when the volume is in a decimeters cube, but it's so easy to get confused. If you remember pascals and meters cube, that's it, you're safe. Of course, you need to do the conversions, but that's why it's important to notice the unit every time of whatever is given to you in the question, because this will help you. So the conversions. We saw before the conversion between centimeters and decimeters cube. Meters is just after decimeters cube, and there is a 10 to the 3 difference. In fact, the decimeters to meters is times 10 to the power 3, while meters to decimeters is 10 times to the power 3. So minus 3 divided by 1,000 times by 1,000, which means that centimeters to meters, there is a difference of 10 to the 6. Okay, 1 million, because remember that the cube makes that difference of 1,000 for each step. Kelvin are calculated as centigrade plus 273. Let's look at this worked example, and you will see that the application is really simple. The only difficult thing is the unit if we have to do any conversion. If not, well, just notice them, okay? Really learn how to notice the units. So let's read it through. Okay, first thing I would suggest you to have the equation clear is PV and RT. We need to calculate the pressure, so let's rearrange for the pressure, nRT divided by volume. Second thing, units, or you can find the moles if you need first, so just notice the values that you're given, and that's where it can be helpful to highlight. Remember to never over highlight things, so in this case I would suggest you to where's my pen here? I would suggest that you highlight, well, you have what are you given, the mass, and we have nitrogen gas, and then we have the volume, then we have the temperature. That's enough to highlight. After having rearranged the equation, we can notice the things that we have and the things that we don't, and we will notice, okay, in this case, we don't have the moles, so that's what we can calculate. And it would be 0.89, which is our mass, divided by the MR of nitrogen. That's why it's helpful to write the symbols as well, because we know nitrogen is one of these diatomic atoms, so we need to know that it's times by 2, it's MR, so the MR of nitrogen, it's 28 in total. This gives us the moles. Then, after we have the values, we can check the units. In this case, they're all correct. Meters cube, Kelvin, moles, and gas constant. All good. And we can just follow with the calculation. There are a lot of numbers involved, so make sure you put the correct brackets or do it step by step. Okay, because it's 1 second to get it wrong in the calculator. Okay, that's why it's important to do it slowly, double check. If you're not sure about the value that you get, you can do it a couple of times and check if you get the same value. If not, well, doing a third time and see which value you get. Okay, it's your turn to apply this pause and then play when you're ready. If you're ready, I am too. Okay. We have moles of this gas. We have the volume. We have the pressure. We have the gas constant. Ideal gas equation, this time we have to calculate the temperature. Correct units. Okay. First, PV is equal to nRT. We need to calculate the temperature, so we need to do the correct rearrangement. Of course, is PV divided by nR. If you have any issue with the rearrangement, tell me and I will help you. Okay, write a comment or text me, because that's a really important one. But for now, I will assume that you know how to do the rearrangement. We can look at the units. Do we have them right? Okay, what unit do we have to remember? Pressure. Pressure is in meters cube, and the pressure is in pascals, and volume is in meters cube. Temperature is in Kelvin. Okay, we have them. Oh, we don't have them right. There we go. So this must be 101,000 pascals. Okay, and now we can plug the numbers in. So temperature is equal to 101.3 times the volume we're given there, 0.0235, divided by the moles, we're given that 0.547 times the R constant, 8.31. And this will give us 522 unit, very important, Kelvin. Yeah, if you don't remember, notice you have the hint there. You know it's in Kelvin because somewhere in the question you have that written. Okay, I hope this is clear. Yeah, let's move on into the next equation. Let's talk about percentage yield. This expresses a percentage, the amount of product you obtained in an experiment relative to the amount you were supposed to get. So it's calculated as actual yield over the theoretical yield times 100. But let's understand this a bit more. Actual yield is the amount that you obtained in an experiment, while the theoretical is the amount that you calculated from the stoichiometry of the reaction. So you know all of that mole ratio moles, basically is the maximum amount that you can get, while the experiment is the one that you got minus all of the steps that lose some mass here and there, or if the reaction is not complete, because it's rare that in an experiment you get 100% yield. There are always some steps that loses a bit of mass here and there. Okay, so the tricky thing is to understand which value you're given in the questions, if it's actual, if it's theoretical, and which one therefore you need to calculate. So let's look at this example. Ready for a moment, and then I will walk you through it. So we're given a mass here, 5.5. You need to interpret what that is. And from the wording of the equation, of the question, you would understand. So this is if the mass produced, that's the keyword. That's the actual yield, because produced, obtained, those will tell you the actual yield. So if we have the actual yield, to find the percentage, because that's what the question wants, we need to get the theoretical. And the theoretical, remember, is that maximum amount. So we used mole ratio moles. In fact, the first thing we can do here, find the moles of what we're given. In this case, we use the concentration equation, volume, concentration. We can find the moles of the hydrochloric acid, because those are the values that we have. And of course, remembering the changing the volume into the correct unit. So in this case, we get 0.1 moles. Second step, ratio. The ratio between the hydrochloric acid and the product of our focus is copper chloride, so would be 2 to 1. 2 to 1, therefore that would be 0.1 divided by 2. We get this value. So now we can find the mass by rearranging the equation of the moles times the MR is equal to the mass. This is our theoretical yield. If you obtain that, notice that also makes sense. It's a bigger value, so you know that that's going to be your theoretical. Actual over theoretical times by 100. And this is the yield that you get. Okay, so now is your turn into one that may require a little bit more interpretation. Pause and when you're ready, play, and I will walk you through it, and you will check if you answered right. So, the mass of phenol to the decimal point produced from 3.3 grams of benzene is. So we're trying to find, guess what? If you understand produce, it only refers to the actual yield of this. But we start with this. This is a bit tricky just because you know that you cannot compare things in mass. You always need to turn them into moles. So first step, we would find the moles of benzene by doing 3.9 divided by 78. So the moles of this would be 0.05. We know that the ratio is 1 to 1, but we get 80% yield. So without even needing to rearrange the equation to find the actual yield, we know that the yield tells us that the proportion that you got, like the percentage. So we can just find 80% of this 0.05, because you know that you will get 80% of this, which is your theoretical yield. So this will give us a value of moles of 0.04. Value of moles 0.04, and this is our actual yield for this step 1. But this is also the theoretical yield of step 2, because that's the amount that we got from that ratio 1 to 1. That's the maximum amount we could get. However, we know the yield 90%, so we know that the actual yield of our product will be 90% of that 0.04. So this would give us 0.036. I know it's in moles and we need the answer in mass. So we will times that by 94, and the correct value would be 3.38. Did you get it right? If not, let me know if you don't understand any of the correction, and I will help you more. Are you ready for the next equation? Atom economy. So atom economy express as a percentage the amount of a reactant that was converted into a useful product. So this value gives us an idea of how much waste it's formed, because the higher the more waste product is formed in a reaction, the lower the atom economy. So this is a really important value to discuss the sustainability of a reaction. So it's calculated as the MR of the desired product divided by the MR of the total reactant. But think about something to make the calculation faster. Total reactant is the same as the total product because the equations are always balanced. So I'll walk you through this first. Read it. So this is our desired product. If we follow this equation, because this makes a bit more sense in terms of definition, we find the MR of the desired product. Here it is. MR of the total reactants. Wow, but it's an effort. And then we use this equation to find the atom economy. But just remember that if you have the desired product, you can then just add in the other product, because overall the MR of the total products will be the same. Okay, so think about how to do it faster, and you will need it for the equation that now you need to try. Pause, play when you're ready. So which approach did you use for this equation? What do you think? Sometimes the fastest way is not the right one, because we can just stare at those equations, but it's really difficult to compare them, which means that if you need to compare them as atom economy, well, you know the equation, straightforward, just calculate each of it. So carbon containing products for each equation are those ones. And I would do it. I would find the atom economy for each equation, and then you will get the correct answer straight away. So it seems like a longer process, but at the end, you can clearly see the answer. So I calculated them as 71.42%, 56%, 82%, 92%. And here you just need to be fast in finding the MR. And then, well, think about what I said about total reactants or total products. Anyway, the correct answer is D. The next, we're talking about empirical and molecular formula. So, molecular formula is the actual number of atoms in a compound. So if we have it's basically the full number, so C4H10, for example, while the empirical formula is the smallest ratio between atoms in a compound. Okay, so this it's basically if the molecular formula can be divided by any number. In this case, C4H10 can be divided by 2, so C2H5 cannot be divided any further because we only want the whole ratio. Okay, so the empirical formula can be found in this way. Read one moment the question, and then I will walk you through. So remember that we want to find the ratio between the elements that make up a certain compound. That's why we need to find the moles. Remember moles, ratio, moles, always that. So the first step for this is always finding the moles. And sometimes it's just a ratio, so it doesn't matter if you're given the percentage. You can just consider this as the mass, as the whole percentage. Sometimes, like in this case, you need to do a little bit of interpretation because you're not given the percentage of the other element, oxygen, but you can find it by doing the percent divided by minus the amount that you have. So the first step, finding the moles of them, you can use the percentage. We have 2.86 for both. Divide the moles by the smallest one, because this gives you a ratio already. And if you have a whole ratio, like in this case 1:1, great, easy. If you don't have a whole ratio, then if a decimal is obtained, you can just multiply to get a whole ratio. So this is our molecular formula. It's our empirical formula, OF. But we want to calculate the molecular formula. And to do that, we need the molecular mass of the compound, the whole compound. Yeah, because we can always find the MR of the empirical formula. So that's the next step. And in this case, it's 35. And then we have the MR of the molecular formula. And I wrote this as little x and little y, because as we know, the molecular formula are multiples of this empirical formula. So we just need to find how many times, if any, is bigger the molecular formula compared to the empirical formula. In this case, is 2. This tells us that the empirical formula, the ratio between the atoms, has to be multiplied by 2. Therefore, we have O2F2 as the molecular formula. Now it's your turn. So do you remember the steps? It's really systematic, so it's important to be confident with that. But you always know where to start because we always have the ratio. So let's do it together. And writing it down in this case, because there are a few steps, is always better. Moles of nitrogen is 2.8 divided by 14. Moles of oxygen is 8 divided by 16. And that gives us, I don't have the numbers ready, so I'm going to do them with you live. 2.8 divided by 14 gives us, where's my pen? Gives us 0.2. Moles of oxygen, 8 divided by 16, 0.5, right? Yeah, got it right, 0.5. So of course, this doesn't give us an idea. Well, actually it does, but let's see, we can also get a full ratio just to do all the steps. Next step is divided by the smallest number to get a ratio. And this gives us 1, and this gives us, so 0.5 divided by 0.2 gives us like 3, I think, no, 0.2, gives us 2.5. So as you can see, we don't have a full ratio. It's 1 to 2.5, which means that we need to multiply them as many times as we need to get a full ratio. And if we multiply both of them by 2, we get 2 to 5. So 2 for nitrogen, 5 for oxygen, and this is our empirical formula. Okay, to the next one. The last calculation for this lesson is water of crystallization. So first of all, the definition is water that is chemically bonded in a crystal salt. As in expresses this in this way: salt with a little dot, and then this it's the whole ratio of the amount of water that are present. Okay, so we have 1 molecule of salt for a certain number of molecules of water. Okay, let's look at this example. Read it and then we'll do it together. So here it's important that you interpret the data that you're given, because you can either work it out in this way, like in some question you have it like that as a mass, so it's heated and then you lose the water, and you can calculate the mass of water and then do always mole ratio. Yeah, it's always very similar. And otherwise you can play around with the MR. Okay, so let's look at this example anyway. We have 4.38 of hydrated zinc sulfate, hydrated, so we're talking about the whole salt, and obtain 2.46 of anhydrous. This means that dry, means all the water is gone, which means that this amount is just the salt. If we have the hydrated and the dehydrated one, by doing the difference, we can find, the first step, the mass of water removed. Then we can find the moles of water, and then, you know what, the ratio. It's very similar. Find the similarities with the empirical formula and molecular formula that we did before. So mass of water. Moles of water divided by its MR, so would be 0.107. We can also find the moles of the salt because we know that there is one salt anyway, and we have the mass of it, 2.46, and we can find its MR. And then again, we can find the ratio by doing the moles divided by the smallest one. So the smallest one is always the salt because that should be 1. And then divide the moles of water divided by the moles of the zinc sulfate gives us a whole ratio number. Hopefully that is the amount of water. Okay, not too difficult, I hope. And now try. It's your turn. The steps. Find the moles of the salt because we have the mass of solid remained. What is that? Well, that is just the salt. I'm going to write down the formula. That is the solid that remained. Here it's a bit of interpretation, but we know that the water would evaporate. So this is the mass of just the magnesium sulfate, yeah, the anhydrous. This is the hydrated one, which means that we can find the moles of the salt, which are calculated as divided by, this one divided by the MR of magnesium sulfate, I got 0.056 moles. Then I can find the difference between the two because this is the mass of water that remained. So the mass of water that remained was, I'll write it down here, 7.06. And I can find the moles of that, which was that divided by 18. I got 0.39. And now we can get the ratio again, smallest, the salt it's 1, and the water this divided by 0.056 to get a full ratio. I got 7. I hope you got that too. We are at the end of our amount of substance long lecture. And there are some tips for calculation. Let's read them through together. First, identify the equations necessary before thinking about number. Okay, write them down on the side of the equation. Look at the units if you need to identify the equations, okay? Or if you need to do conversions. So it's really important that you build these habits of slowing down your mind when you read the questions for calculations. Third tip, label the steps you're taking. Number without a unit or a sign have no meaning when you look back at them. Imagine that this question, I had just 0.056, 7.06. How much effort would be to look back at them and try to identify what they were? But if you label them just like this with a little label, the chemical formula, yeah, or the substance that you're finding, and the unit, this number suddenly have a meaning. So if you look back at them, it will make a lot more sense. And in an exam, this helps you in following along the steps much better. Fourth tip, if you're stuck, just think about moles, ratio moles. This may give you a starting point. Okay, always, as you notice in all the calculation we've done, at the end we start with the moles, and then somehow we need to get the ratio. Sometimes we don't need it, but keep this in mind: moles, ratio, moles. Once you're finished, reread the question to check if the answer is asked with specific significant figures. Okay, if you have any questions about significant figures, please send me a text or comment, because I haven't specified in these questions, but we will see when we do exam questions together. Okay, so always, when every step, I would suggest you actually every step that you do in the calculation, then look back at the question, making sure that you follow the right, just the right step to keep it all in mind, the overall picture, yeah, and all the steps that you need to take. Okay, so I hope this helps. And now it's your turn for the practice questions. You have the solution and then the checklist. Okay, if you have any questions, contact me.